Welcome again back to Web3 Builder workshop series with Web. Last time, what did we talk about? Solidity. We talked about programming and smart contract in Solidity. What are smart contracts? These imagine the blockchain as a smartphone. These smart contracts are essentially apps that you can install on the smartphone to make things more useful. Some examples include, NFTs, new tokens you can launch. Last time we launched, your own token. You can use your name to name some cryptocurrency, and you can do decentralized finance. You can do governance stuff. Everything you can imagine, everything you can make happen with code, you can basically do it with the blockchain computer, Ethereum. And this time we're gonna sort of dive a bit deeper into sort of other things that happens on Ethereum, specifically security, scaling, and bridges. So first, we'll talk about Web3 security. Okay, cool. Web3 security, just like in Web 2, where you have security concerns. So you have, what's the problem here? It's like hackers, right? They hack you, hack your code. They can, clear your Fortnite account. Or in blockchain case, right? You often have a large amount of money, or cryptocurrencies in someone's account, in some smart contract, so that the implication of getting hacked is sometimes far greater. It's, I guess, a good analogy would be like a bank getting hacked. So these are very lucrative targets. So when a hack happens, it's pretty bad. So here we have our first example, the DAO failure. The DAO is one of the first ICO standing for initial coin offering. So essentially this is, in the early days of Ethereum, it's like 2016, 2017, right? And so there's a group of people, they're like, great, we have this new technology, and now we can sort of run things by a smart contract on the blockchain. So they decided that, they essentially want to raise funds for investment. And they're like, okay, everyone just send us your money and we'll invest it for you on various projects, except someone hacked. So people all sent money to their account, right? And then their account got hacked. So how much was lost? A lot of money was lost. And then, but what's interesting is that the hacker actually came out and said, these words. So the hacker believes that this person made use of this feature. It's essentially how they hacked the contract, and rightfully claimed 3 million whatever Ether, and then actually thanked out the reward. Why is this, right? Because the DAO says that essentially whatever is in their code is, that is it. That is, how things are meant to run. They also encoded, other governance rules, how people did make decisions and whatever, but that also includes one of the bugs. So the hacker, in their interpretation, they're like, you guys set up this, this feature, this this is not hacking, I'm not exploiting your code, it's just something that's there that I'm just, if the bank's back door is open, I just walked into the bank and took the money out, like it's designed for me to do that. So how could they potentially change this, right? So on the blockchain, we know that the block, keeps going forward, and it's really difficult to sort of modify what has happened because of what? You guys remember? What cryptography concepts made it immutable? Okay, it's hashing, right? You chain the hash together so that it's really difficult to change what happened in the past. And to attack the network, you need a 50% plus of blockchain nodes to agree to do this. But what happened for the DAO hack is that the attack was so detrimental to the ecosystem, because now you're just investing all your money, invest a lot of Ethereum into this bank, and then the bank got hacked. Now, would you ever do business with this bank again? You would not, right? Like, you lose faith in this forever. So that would be very detrimental to the blockchain ecosystem. So what ended up happening is that there was a hard fork. So because so much money was withdrawn, right? People lost confidence in this, and then ETH price dropped 25%. but then they decided to make a hard fork. So essentially, right, okay, so we have this blockchain where the hack happened, and now we're like, okay, never mind, let's just go back in time and try to fix it. So now essentially they need to get more than 50% of every Ethereum participant to agree that, okay, let's just wipe out this history and recreate a branch of this blockchain. So this new blockchain is now what we consider to be Ethereum, whereas this old one where the hack happened is now called Ethereum Classic. Ethereum Classic believers and people who still sort of make new blocks and participate in that network, they believe that, okay, whatever happens, as bad as the hack gets, we cannot change the history of blockchain because that's dangerous. Because if you change it once, who is to say that you won't change it again, right? That's problematic because that's not what blockchain is about. But yeah, no one uses Ethereum Classic nowadays. Everyone uses the one where we fix the hack. And I guess nowadays, even though there are still hacks going on, but we don't try to fix it because usually, like, one is that we have so many people believing Ethereum and then we change it again, it would affect the confidence. And second, I guess the hack was just not as great of a scale nowadays compared to what happened then, because we are a lot better at writing smart contracts, or the smart people are a lot better at writing smart contracts. But here's another hack, Gym Network. I don't really know what it is, but essentially, so nowadays we have professional sort of bug catchers or auditing firms. They look through your code and make sure there's no bug. But even then, that's not a foolproof way to do things, because Gym Network, they're a DeFi network, so they have a lot of money in it, so stakes high. So they hired Certic and Pexio. I know Certic is a very reputable firm that checks your code and makes sure nothing's wrong. But what happened is that after their code is verified, okay, this is good, no bugs. 2 days, they added some code to it, and then the code they added introduced some bug, and then they got hacked. So the one thing to know there is that even though now blockchain code gets audited, and sometimes you go to a website, they say, oh, our code is so safe, we got audited by like this 10 different auditing firms. But as long as they're making continuous updates to the code, and then it's really hard to guarantee that the updates they're making to the code, they're constantly getting audited, right? So because every time you audit, you have to pay a large amount of money, right? And then if you're like a traditional software firm, right, where you're pushing updates every day, like I don't know if you guys are familiar with the CI/CD concept, continuous integration, continuous development, deployment, right? You're actually pushing changes maybe every 30 minutes. How can the auditing firm catch up to the speed of that? Impossible. So to keep in mind, there's always a trade-off between security and the speed to patch bugs or add features. Here's another example. This is Uncle Auction, which is the NFT minting contract, something metaverse. Apparently, it's really popular. And then what happened here is that they introduced, so essentially there is a mechanism where people are allowed to deposit money, but then when something happens, they can withdraw the money. But the hacker essentially was able to plant a bug, not in the original, the hacker wrote a smart contract that sort of interfaces with the smart contract that is deployed, the NFT contract, and then was able to essentially make everyone unable to withdraw their money. So everyone's money is stuck there, and this leads to some sort of clever engineering, the property of EVM. But the hacker actually was pretty nice. The hacker said that this is why your contract is faulty, and you guys should admit that this is wrong, and I would remove the block on people with withdrawal, and you guys should go ahead and fix the code. Except the company that launches this smart contract, they're like, no, this is not a bug, it's a feature. So the hacker just didn't remove the block, and people was not able to withdraw their money. Only after a while, the hacker removed the block because of the community pressure. But even then, after people were able to withdraw their money, the company originally, they charged a fee on sort of transactions, right? So at the end, the company and everyone else got their money back, but the company didn't get any money back because the bug is in such a way that the company gets their own fund blocked. So yeah, I guess the takeaway there is to if there's a white hat hacker, asking to admit your mistake, just probably do so. So how do you prevent web security problems or Web3 security problems? First, there is a class at UPenn where you can learn about Web3 security. So understanding what are the common patterns of getting hacked, what are some vulnerabilities in your code, and then know how to fix them, right? And the second step is sort of relates to the problem with auditing firms. Even if you have people to do audits, because you're you're frequently pushing out updates, it's really hard to have the auditing to catch up with the speed of your new releases. So sometimes you need to rely on software tools. So you tell the software, how does my code supposed to function, and run these automated tests on every version that we publish. And that's another way to ensure there's less bugs or you catch most of the bugs. Yeah, and lastly, once you publish your code, there's another way where essentially it's called bug bounties. I don't know if you're familiar with this concept. Essentially, you pay people to find bugs in your contract, except and then if they find a bug, they report to you rather than hacking your contract. So you just pay them some amount of money. Usually it's like 10%, 20% of the value that could be sort of stolen from the hack. So it's actually very lucrative. So if you guys are interested, definitely look into this industry, because if you find a bug that, whose exploit could cause like 200 million being lost, then if you get 20% of that, it's a good amount of money. Yeah. Cool. Next part, we're just going to talk about scaling. Scaling is probably a concept that you would encounter very, very frequently in blockchain in general and Ethereum specifically. So why do we need to scale? This is the graph for the number of transactions processed by Ethereum. So one transaction could be a simple A transferring money to B, or it could be A minted an NFT, or it could be, A borrow some money, the list goes on. And this is the number of transactions per day. You see that the peak, the highest point is probably, I took this screenshot yesterday. The highest point is probably close to 2 million, 2000K, but then, it averages around 1.1 million per day. So every day there's like that many Ethereum transactions being submitted on chain. So probably a lot of them are submitted by hand. So last time we were able to set up MetaMask. So, if you click transfer or approve, usually that's one transaction, but also a lot of these 1 million transactions are automated by computers. So maybe like trading bots or whatnot. Why do we need to scale? Because Ethereum handles 1.1 million transactions per day. What about Visa? Visa handles 150 million transactions per day, right? So even if Ethereum just want to capture the market of transactional payment, it needs to be able to scale up 150 times. And that is just Visa, right? What about MasterCard? What about American Express, right? Just in the category of payment, if Ethereum wants to capture that market, be able to support transactions, and to scale up 150 times, maybe times 3, 450 times. Yeah, sorry, animation is screwed up. Yeah, and then Ethereum is not just about payment, right? Ethereum also could be about gaming. It could be about banking and other apps, right? Imagine people actually executing, more than just paying stuff. They can be executing stock trades, option trades. They can be playing games where, imagine Fortnite. Fortnite's daily average user is probably on the order of 5 million users. And then 5 million users don't just execute one transaction. 5 million users needs to constantly be, updating game data, right? So that could blow up very, very quickly. So we definitely need more capacity if we want to take advantage of blockchain computer. This, what does it offer, right? Security, immutability, and all that. The question is, even though we are at 1 million per day, but is that the capacity? Like, are we actually bottlenecked by Ethereum, or is it just us not having enough demand, right? So currently Ethereum is around 11 transactions per second, if you do the math, right? But the max recorded Ethereum TPS, so transactions per second, is actually 93.01. But 93.01, let's consider that. What happens when there is a lot of demand in market? What happens? High demand, Econ 101. Come on, guys.
Price goes up.
The price goes up, right? So if you have limited capacity, and then your demand goes up, let's say 9x your demand, then the price goes up by a lot. And in the case of Ethereum, right, a lot of these high TPS moments are often where there's an NFT project release. Everyone believes that if they get their hands on the NFT, they can become a millionaire overnight, right? So that at those times, the gas fee, the transaction fee, and how much it costs to run the EVM gets very, very high. So it could cost a couple $1,000s to execute one transaction, if not more. So by increasing the overall capacity, we're also able to lower the price, even when there's a lot of demand. So what's our target in terms of throughput? For Visa, if we want to reach Visa's average TPS, we need to scale network by 150 times. If we want to reach Visa's theoretical maximum, we need to scale the capacity by 2,400 times. And then if we want to replace financial infrastructure like the payment, the trading, the bank loan, and whatever, right? You probably need a 10,000x the Ethereum throughput to replace the financial infrastructure. Yeah, and so as I mentioned, right, there's also a positive feedback loop. If you have more throughput, more capacity, that also means that per transaction, the price goes lower. So if the price of using EVM goes lower, then at one point there's no reason people not use blockchain to do their things rather than a Web2 more traditional infrastructure, because they get the same thing cheaper, but then it's more secure, and you don't have to trust anyone that can lie to you. Essentially, all that is to say that we do want to scale. And at this point, we are so far away from where we want to be that we want to sort of find every possible way and sort of multi-pronged approach to us to improve the scaling problem. What's stopping Ethereum from going faster? First of all, it's the consensus. It's sort of, why do we need consensus? It's security, right? We want to make sure that all these people, tens of thousands of computers, blockchain computers, Ethereum nodes agree on a certain transaction. And we have to have this. If we don't, blockchain loses its purpose, right? Then blockchain is no different than anything else. And the second part is the fact that blockchain is a distributed system. That means like you actually have computers located in all over the world trying to talk to each other. And this part is decentralization, right? If we get rid of that, we only have one computer, then someone just need to hack that one computer and they can take over the entire blockchain. And the problem with distributed system is that you're actually limited by the physics, because if you want to talk to everyone in the network, you need to send, over internet a packet, sort of, say a word to all these computers. And then to travel all these distances, travel through all these wires, you're ultimately limited by the speed of light. You cannot get any faster than that, right? Assuming you have the same amount of computers located all over the world. And these are the two reasons that what Ethereum is, not faster. So Vitalik, the inventor of Ethereum, or co-inventor of Ethereum, proposed this blockchain trilemma. So essentially, the three things that we want to achieve, scalability, decentralization, and security, you cannot have all of them together. So on the decentralized and secure side, for example, Ethereum, we have sort of this bottom edge, right? But as you move to the other side, sacrificing one of the attributes, you have other solutions such as multi-chain systems, the high ETPS chains, which are usually one computer running the entire blockchain. Very terrible decentralization. So what are some options? There are two general categories. We have one category where we're just improving Ethereum, so make the Ethereum code better algorithm. And the other category, which is like, okay, let's look beyond Ethereum and how do we make blockchain in general go faster, right? So first part is sort of Ethereum on-chain scalability. So first part of it is proof of stake, which we have already finished. And what's good about proof of stake? First, it's more green. We don't use computer to solve arbitrary cryptographic puzzles for no reason. And second, you have more predictable block time. So for something like Bitcoin, the block time often is it depends on the hash power, sort of how much computers are in the network. But with Ethereum POS, you actually have a really fixed, is it 12-minute interval that is sort of like you specify that because you're not constrained by computers computation. And that leads to the third point, right? Right now, the Ethereum's sort of 10-ish minute, 10 to 12 minutes arbitrary block time is limited by security, because if you have them any shorter, it's really you have to sacrifice security. But it's not that you're actually like sort of trying to solve a problem, and if you have any less time, you can't solve that problem. So it leaves us sort of more freedom to put more creative design and better technology into this. The second part of on-chain scaling is sharding. So what is sharding? Imagine you have 1,000 people and you're trying to have them vote for president, right? So rather than having 1,000 people in this room shouting at each other and really difficult to sort of tally up the vote, you essentially split them into 10 rooms. And now you have 10 rooms of 100 people to deal with. So now you just need to coordinate 100 people, which is a lot easier to deal with in each room, and that happens at the same time. And at the end, each room just take their number, and then 10 people aggregate their answer together, and you have the total net number. So this is sharding. So rather than having one Ethereum with tens of thousands of computers, you have tens of thousands. That's about right. That's the right ballpark. You split it into multiple computers and have each group come to consensus, agrees on something together, and then they have someone else to report to get the final answer. So yeah, so this is an illustration of what shards look like. 1,000 nodes split into 10, 100 nodes, and within each of those, they're able to come to a consensus faster and cheaper. And faster and cheaper, that also means that given the same time, they can do more of it. The last thing is data availability sampling. So essentially, it allows Ethereum to be a bit more decentralized by allowing you to run an Ethereum node on your computer or even your phone. So it removes the need for the traditional approach, which is you have to download the latest block and then look into it and verify. Instead, you use advanced cryptography. That's so much of blockchain is just like black box advanced cryptography. Essentially, you don't have to download the block anymore. You only need to sort of do rather trivial computations, and then you're able to verify the latest block. The second good thing about this is it separates compute and storage. So if your computer is responsible for both compute and storage, that is more work to do than you're just responsible for compute. So data availability sampling also allows you to sort of move the storage off to somewhere else, obviously not in a secure manner, but then Ethereum can just focus on making sure the computation is correct. Now, we're also going to cover off-chain scaling. So this is sort of, now we're no longer improving Ethereum itself, but then let's add something onto it to make it faster and run better. The first one is the general category of rollups. So essentially, imagine you have 100 people sitting in this room, and this room is capacity 100 people. But then what if you squeeze like 100 people onto one seat, right? Then you're able to 100x the capacity of this room. So here's another example. So you have Ethereum. which is running at its max. But then you buy another computer, right? This computer gets to process a lot of the transactions, and it can process 100 transactions, and then simply create an answer or a result, and then send that one answer to Ethereum. So that is how rollups in general works. But the problem with this is it's less secure, because for Ethereum we have these tens of thousands of computers sort of verifying that everything's done correctly. But now we just have one computer sort of responsible for itself. It's really hard to guarantee that that one computer is doing everything correctly. Oh no. Oops. So there are two ways, it's not this way. There are two different approaches to doing rollup. First is optimistic. On a high level, optimistic is essentially we have that separate computer, right? We're just going to assume that computer does its job and computes everything correctly. And only when we have another sort of smaller committee, the smaller committee would sort of look at the computer, and then when there's something wrong with that computer, they would come out and be like, yo, there's something that's incorrect, and then we go fix it. But we initially just accept the results from that computer without sort of much sort of verification. And then we just have a very small committee. And this is not sort of on the order of tens of thousands. This might just be a committee of 5. And 5, it's really easy and cheap to sort of create, to do the verification. Yeah. And the second part to this is zero knowledge. So rather than trusting that one computer to do its job, processing 100 transactions, we actually ask that computer to generate a mathematical proof that you are doing these 100 transactions correctly, right? How do you create that proof? Advanced cryptography, obviously the answer is. So it actually generates a proof, and the proof is evaluated on chain. So in that sense, the verification step of the proof is secure and can be trusted. Yeah, but the problem with this is that we actually don't have that advanced cryptography. This is sort of an idea. We have components of it, but we don't have it sort of fully realized. Up to this point, we really can only, we can't really realize, the full capacity of EVM, which is running almost arbitrary computer instructions, but rather it can just execute transaction like from A to B, right? You have 100 A to B, B to C, C to D, whatever, and it's able to aggregate that into a verifiable proof and verify on chain. But we are sort of moving in that direction, in that we have technology and companies sort of almost there, such that the computer on the side can execute arbitrary sort of smart contract or code. Yeah, and lastly, we have sidechain. Sidechain essentially is, rather than this one computer sort of splitting the work for the Ethereum to make Ethereum faster, but then sidechain is completely, okay, let's just have blockchain number 2, maybe like Ethereum number 2, and then let's make some connection. Let's have like, a few connections back to the original Ethereum. For example, Ethereum can send money to me, and I can send money back to Ethereum. Ethereum can send data to me, I can send data back to Ethereum. So in that sense, you just have, if Ethereum's capacity is 100 transactions per second, then we have 2 of them, the capacity becomes 200 transactions per second. So you're able to scale linearly. Now, even better, for a lot of these sidechains, they're not as secure as Ethereum. So they're like, okay, security is not important. So we're just gonna sacrifice decentralization. Let's just run everything on 5 computers or 10 computers, right? And then I'm actually able to go faster, right? But the problem with that is obviously security, right? So if you are relying your this second blockchain on this new and weaker consensus and security model, then it could potentially bring sort of bad reputation to the entire blockchain ecosystem. And even though you're scaling, but like the first 100 TPS and the second 100 TPS or 200 TPS are different, because those are quality TPS, quality transactions, safe transactions, whereas you're just adding not safe transactions. So to sum that up, optimistic rollup, it's great. It's really fast, and it supports the same thing as EVM Ethereum. but it's centralized and potentially less secure. So it's like not as decentralized and less secure. And the problem is, what if a mistake is made? So even though we talked about, we have a committee of 5 for catching the mistakes, actually in implementation, they have never had to solve that problem. So they actually don't have the solution for that. So if optimistic rollup screws up, like that's like, we don't really know how to deal with that. Like that's just a undefined case. Like it's like you have an else statement and then it just breaks your code. So that's the problem with optimistic rollup. But the good thing is like it's usually very reliable. How about ZK rollup? Rollup is centralized, but it actually doesn't have any security implications because it generates a mathematical proof that you can prove on chain. So it's centralized, but it's not less secure. But the problem with that is we just don't have the technology yet, right? Like we'll probably take another 5 to 10 years for it to completely work to the same degree that Ethereum works. Although at that point we'll have a lot more capacity. The sidechain option is also centralized and less secure, but it's basically a separate blockchain. So like it's no longer, in a sense, it's not like scaling Ethereum anymore, but it's scaling the overall blockchain ecosystem. And the security of those blockchains are completely reliant on their own consensus algorithm and usually are weaker. So you're almost just diluting the security of the entire blockchain ecosystem. How about the actual directions we're taking as an industry? So we actually see a lot of sidechains because people are like, okay, Ethereum is just like, too conservative, too safe. We don't actually need to be that safe. We're okay with, a bit more tolerance for risks, right? So industry is actually going with, a lot of sidechains. For example, a name you might recognize is Cosmos. Cosmos essentially is a piece of software that allows you to, just like how we roll our own cryptocurrency, right, on Ethereum, Cosmos allow you to write your own blockchain very easily. And it's just like, you can execute 10 lines of code and then you have your own blockchain. So that's the second point. A lot of people actually don't care about decentralization and they don't care about security as much. So optimistic rollup also has, and very popular right now. There are optimistic rollup services that offers you one click, you have your own rollup. So there's a company called Constellation that's doing quite well. And then there are also people who say that I have a novel consensus algorithm, I have advanced cryptography, right? And then I'll just solve the scaling problem once and for all. For example, Algorand, that's what they say. But I don't know. Brandon, what do you think?
It's a great project. What do you think like Tal Robbins says?
Tal would say that Algorand is the only differentiated blockchain that will be the future. So I think overall, everyone agrees that zero knowledge is the future if the technology is there. So the constraint today is that we don't have ZK EVM. So we're not able to run the full extent of EVM, the smart contract, the apps on a zero knowledge rollup. Rather, we can only do transactions, which is like Bitcoin. So we have ZK Bitcoin, we don't have ZK EVM. So we have options, right? Polygon is working on ZK EVM, and they actually just launched like yesterday. And ZK Sync, they've been running their sort of more transaction-only version for a while, and then they're also coming out with ZK EVM. I think they launched probably before winter break, but I don't know if it's like fully there yet. And then the other company includes Starknet, Sequoia-backed, big, huge Israeli company, and Scro is a Chinese company that is delivering a lot of very promising results on ZK EVM. Cool. I'll hand it off to Brendan. By the way, any questions? I think today we switched gears, sort of trying to cover, words that you might encounter when you talk about blockchain or read blockchain stuff. Okay, cool. You can go.
Oh yeah. So for Algorand, right?
Right.
Did they ever like release their algorithm or like how it solves every problem or like?
Yeah, I think so. I think a lot of the core consensus code are open source.
Has anyone actually verified their claims or?
I think so.
So the protocol they use is pure proof of stake, right?
Okay.
It's basically you send packets with like a certain threshold of validators that are randomly chosen each block. And there's a lot of research paper that analyzes like, I guess, like the feasibility and like the utility that this pure proof of stake system creates. I think I can link you up with some paper that someone, wrote. It's pretty helpful. Just ask me after class.
The problem with consensus algorithm is like you don't know if they're going to work unless you've used them, right? The same thing for proof of why is Bitcoin still staying with proof of work, right? It's like people are literally saying that because this worked for 10 years, so it's literally better than the algorithm, even if they're better that has worked for 1 year. Because a lot of this is like you need to run simulations rather than like do a mathematical proof to make sure it works.
So I was just wondering, like, I still don't really get why like side chains are like less secure. Like if they implement like similar like security protocols to like Ethereum, for example, like what makes it like less secure to have more?
In that case, it's not less secure, right? Sidechains are only secured by their own consensus. But then the problem is like sidechains don't usually implement Ethereum because there's already Ethereum. If they're the same price as Ethereum, same speed as Ethereum, same scale as Ethereum, no one's going to use them. They're going to use Ethereum.
Okay, so they just kind of like just by definition are like worse versions.
So by definition, they're not worth versions, but by like market reality, they're usually worth versions because they have to differentiate themselves by saying we're faster, cheaper, right? So but like trilemma, you can't be faster and cheaper without sacrificing security.
Yeah.
So at the end, you're just sacrificing security.
It's also like a very important thing you have to notice is that like with smaller networks, right? Decentralization, a lot of the time the security is made up of like how big your user base is. The more nodes on a network validating the transaction, the more safer it is. That's why like Bitcoin is still, I guess, undoubtedly the most valuable network at the moment, simply because like it's just been so long. It's the oldest working blockchain, and it accumulated a huge amount of like user to secure the, I guess, like the security of the network. If you have like a smaller network, even with like a drastically, I guess, like groundbreaking new protocol, if you don't have enough users, if you don't have enough like nodes to support the network, then it's just not going to be as secure as Ethereum.
Yeah, so I was actually talking to the Certi people, and they were talking about how so Aptos and Sway, the new Move language-based smart contract chains, they're actually, even though their consensus might be better, but they have a lot more possibility to get 51% attacked just because of the fact that they're young, right? But if they're 5 years in, a lot less possible. So it's often the case that when a new blockchain releases, the company or the organization behind it would have significant control, because if they just let everyone run the node, right? Like at the beginning when there's like 2 computers, I'll just buy 3 computers and take over the chain. Whereas like once it runs for 5 years, there's already tens of thousands of computers, right? You can't easily take over the chain. Right? So that's sort of beyond consensus algorithm problem, but it's more of just a resource problem.
Have you looked into like layer 3 scaling? Because I know Starknet and like ZK Sync, they're like developing projects in that space, and I'm not sure like are they going to put like more rollups or like validity on top of L2, or like is it going to be like another like scaling solution?
It's not that different. It's just like you're just recursively doing this. I think layer 3 generally is like very app specific. So I guess the concept is like you have layer 1, which is like be all and all. This is like you're carving words into stones, and you have layer 2, which is like sacrifice a little bit of stuff, but it goes much faster, but still mostly general. And layer 3, I think the concept is that you just have like really specific stuff, right? Like I'll have a layer 3 solution purely for feeding my CryptoKitties, right? It has 2 instructions: feed and unfeed. Okay, that doesn't make sense, but like that's the point. But in terms of how do you stack one layer on top of the other, what we just talked about, I think is pretty comprehensive.
So I think another project you might find interesting is called the Ton network. It's basically created by the same group of people who created the Telegram. They believe in this society where there's going to be blockchains of blockchain, and each of the block on the blockchain. I know this sounds very recursive and confusing, but it's an interesting technology. I think that might answer some of your question you have about layer 3. So thank you. More questions before we move on to bridges? So bridges, all right. Let's first imagine a world without, let's say, any transportation across the ocean, right? No ships, no airplanes. How is that going to work, right? That's pretty much before, let's say, like Before ships were invented, right, across Navy, before it was like discovered, all these different continents are just kind of locked on their own. They have their own ecosystem, they have their own economy, the goods and services cannot be exchanged across different continents, and therefore they have their own locked total value within this continents, right? So what that means for like people living in this continent is that there's a lot of inefficiency in the system. Because like linking back again to Econ 101, efficiency is like only created if you can efficiently allocate resources across different like stakeholders in a fixed economy, right? But if you don't have that freedom of exchange and that freedom of flow of these resources, there is going to be inherently some inefficiencies in the design of the system. And that's why international trade is such an important concept for modern society, right? How can you enjoy your Japanese confectionaries if you don't have airplanes and sea ships that bring you them, right? There's no matcha, there's no banana. How can you enjoy all these like good things, good utilities that these goods and services can bring from different continents? Well, you need transportation layers such as airplanes and sea ships. And in the same case of blockchain, how different blockchain networks have different protocols, they cannot natively communicate with each other, just like how different continents cannot natively reach each other by, let's say, ground transportation. So there must be some sort of system that allows transfer of value and like goods and resources between these chains, and that's called bridges. So cross-chain bridges, right? Before we dive into like the details of what it is, I would like to introduce a concept called oracle. So an oracle is just any entity that connects the blockchains to any external system. So what that really means in idea is that like, let's say we have an API that tells the current weather of New York City right now. The blockchain itself would not know that because it does not talk to the real life. So someone or some entity or group of entities called the oracles must tell the blockchain that this is the off-chain information. So therefore the blockchain can utilize that information and like, I don't know, do some sort of logic on it, maybe determine the price of Bitcoin if it's sunny or something. So like what that also allows is that Oracle can pass data between different blockchains, just like how I can pass like maybe the seeds of banana from Africa to America, right? They basically can pass data packets across these different chains, but the true problem is how do we establish an Oracle system? What is the infrastructure for creating a secure Oracle layer? And how do we, I guess, incentivize everyone to provide the right information? So, but before we dive into that, let's just talk a bit more about cross-chain bridges, right? So cross-chain bridges just allows the transaction of, let's say, like tokens, NFTs, and even smart contract calls between different like blockchain networks. Depends on how the bridge system is built. It's a very cool concept, but so far it's still not very secure at the moment, which we'll dive into later. And again, Oracle just observe the events happening on both blockchains and just like update the corresponding chain with the updated information. So there are three current main types of bridges that's available in the market right now. The native cross-chain validation, the proof of stake, multi-party computation bridges, and the one-to-one bridge, which I'll be talking about one by one. So what is the native cross-chain validation? It's just kind of like if you have a single project that owns two different chains, for example, Binance Chain and Binance Smart Chain, since you both own it by like or controlled by the same community, it's very easy for you to kind of just modify the protocol on both sides so it talks natively with each other. Like for example, on the Binance chain, they basically what they can do is implement a system in their base like layer 1 protocol to allow them to generate like a summary hash of the entire blockchain, which can be easily passed to the Binance Smart Chain for validation. So how it really works as an overview of how it really works is that it's just really an integrated way of the base layer 1 protocol between two different chains. An example of that will be rollups that Intel just mentioned about scaling, because as you think about it, these scaling like either side chains or just like layer 2 chains are natively trying to design and cater to the Ethereum protocol. This is a native way to, I guess, like establish this bridge and like allow the fast transaction of data between them. And it is trust minimized because you are designing your base protocol based on the original protocol of the source chain. So as long as like the base protocol of the source chain works, then you don't really need to worry about it. It can have a high cost of integration because like depends on like what the source chain destination chain's protocol is. If you have like on a source chain, if the source chain, let's say, is Bitcoin, which you would normally need to, each block time is 10 minutes, and you have to wait up to around 6 blocks for your transaction to be really confirmed, then each transaction between cross chain would take at least an hour. because you will need to reach finality on the original source change for that to happen. Yeah, and it can also be really slow for roll of exits. And proof of stake, multi-party computation bridges. This is the majority of the implementation of like bridges currently that's available in the market. And how it really works is that we have like a third party that comes into play between these two bridges, these two blockchain networks, and say, hey, we're going to be the oracles, we're going to be the validators that facilitates this cross-chain transaction. We're going to be monitoring the data between the source and the destination chain, and we will be the one who has maybe either like a centralized entity or a decentralized group of entities who come to an agreement what the canonical version of the data on the source and destination chain is. Right. So it's just basically you have a, I guess, you have a trustable, quote, trustable, which we'll get onto later, group of oracles that passes on the data between the different chains. So if a transaction happens on chain A, these proof of stake nodes can come to agreement saying, oh, we all saw this transaction happen on chain A. Therefore, some events will happen on chain B. And some example of this will be the Polygon proof of stake bridge and Thorn chain bridges. And again, they can be like the organization who hosts this, like I guess, Oracle infrastructure can either be centralized or decentralized. And there's a lot of problem with centralized proof of stake, like third-party organization. One reason is that because it is now centralized, it's a very, very, I guess, good to attack single point of failure. We have seen a lot of examples where, I guess, centralized bridges got hacked. Either it was because of like some sort of loophole or exploits in their code, or some other random reasons that just resulted in hacks, right? But the benefits of this is it normally has a very like low cost in comparison to native integration, because you only need a small amount of computation from this like group of oracles to facilitate and like monitor this transaction between chains. And this can also be applied to almost any chains, because it's really just about like these oracles monitoring transactions. You don't need to make too much modification to the original like source and destination chains protocol at all. And lastly, we have the one-to-one bridge. So whether or not one-to-one bridges are really bridges is still like a hotly debating I guess topic. And this is truly because at the end of the day, the net transfer value between like chains using the one-to-one bridges is zero, or mostly zero. How it really works is that it's just like a cross-chain swap, in which that if person A sends a value from chain A to chain B, in exchange, someone from chain B should also swap the same amount of value back to chain A. And how they do that is through contract lock values. So tokens, let's say Ether and what is Algorand's token? Just Algo. Right? Yeah. So let's say Ether and Algo gets locked up on like Ethereum and Algorand. They both get locked up. They're locked. They basically get a confirmation that these tokens are locked on each side. And the two users, the two parties that are swapping this token, sends that proof of lock to the opposite chain. Both chains validates that, and then at the same time, the token gets released. It's a really fast system, but again, the downside is that at the end of the day, the net transfer value across the chain is zero. So you can't really truly transfer value across chains, but it is a really good way for you to swap your Ether with Algo or Sol or any other tokens. That's part of this. And one really good company that's currently doing this job is Connext, which they're originally called NXDB protocol. And yeah, they basically provide liquidity on both sides of the chains, which facilitates this transaction of value across these chains. Yeah. So do bridges really work? Most of the times, but it can be hacked. And once it gets hacked, absolute chaos, right? The biggest loss that we have seen in 2022 was the Axie Affinity's $650 million Ronin bridge, right? Axie Affinity is an on-chain GameFi game system, and they have their own currencies. They are linked with the Ethereum network, and the bridge that does talking between the Ronin bridge, which is their own game bridge, and Ethereum is the Ronin bridge. And they got hacked, lost $650 million, took a huge dip in value. And it's not just them, right? Wormhole got hacked. Wormhole is a bridge between Solana and Ethereum, and they're one really good example of a centralized proof of stake bridge, right? They have a bug in their smart contract code, and what that led to their 321 million hack. And Nomad got hacked, Binance got hacked, not necessarily hacked, but just through exploits and just either bugs or I guess human failures in the design of the system. So yeah, because if you have wealth accumulated in one single place, and it's really, it's like a giant prize pool, right? Everyone's looking at this giant like total value lock in this bridge and like, how can I hack this bridge? How can I get this value out of it? How can I just, pull off one hack and never have to work for my entire life, right? 650 million. And if you look at the data, right, in 2022, bridge hack resulted in like the majority of like all the DeFi financial losses in comparison to all the other DEX, like centralized exchanges and everything else. So, and the reason why this is so far, it is still extremely difficult for us to come up with a good design for bridges. Why? Well, here are a couple of challenges with inherently designing a secure bridge system. One of the main reasons, which I personally consider to be the most important reason, is what is the concept of canality, right? Like, what is canon? You have two different forks of a network, and it's just the idea that people come to consensus on one single version of the blockchain, right? As Intel discussed about like the hard fork with Ethereum and Ethereum Classic when the DAO hack happened, there's still some people who would choose to stay on the Ethereum Classic network simply because they believe in I guess that is the true like code is law environment of Ethereum. Therefore, there are two completely parallel networks running when a fork happens, but which one of it is the canonical version that we give to the other chain, which has who has like no information about what is the current status of the source chain, right? So deciding what is canon is a very difficult process. And there's also like the hard fork problem in which that validators are technically incentivized to create forks simply because if they do create forks with like malicious transactions, they can all gain money out of it. There is the assumption that like, as all humans, we operate on the incentive of financial, like, I guess, gains, right? And if this assumption is true, then it is truly like, I guess, impossible to design a proof of stake system in which that like everyone will be possibly incentivized to not hack the system. Because if you think about it, for whoever's that's on a network who is a validator, like they will always make financial gain if they come together and collude and hack and they add money to the bank.
Can a validator be a smart contract? Can like a validator be an Ethereum smart contract?
So what you're describing is either like one-to-one bridge we talk about, which you use cryptography to verify whether or not the source change transaction happened. Right. But as we discussed there, you're not really moving value across. But if you're also describing like let's say the native integration, right? You're still asking like validators or oracles to pass the data packet of the original source chain into the destination chain, so, and that can be modified, right?
There's just no way to guarantee that people do their jobs.
Based on financial incentive, that's why it's still like an ongoing problem. Yeah. Yes.
What do you mean by like no values like actually transferred? Can you explain that part?
So think about it this way, right? You have America and China, right? China is very well known for their tea, right? They make good tea. America makes what are we good at? I don't know. Like we're good at making muscle cars, right? Let's say we want to transfer value between international trade is when two countries trade goods and services across, right? And there, if you maybe study Econ 101, you might know there's like a surplus and deficit of trade. What that really means is that like when country A transfer value to country B is not giving like the same amount of value back to country A. So essentially, value is leaching away from one country and flowing to the other. This is technically the case for America after a lot of recent, I guess, like wartime events. Not gonna discuss in detail what that is about, but you probably understand. But that's not the case for the one-to-one bridge, right? Because for the one-to-one bridge to work, there's always going to be a buyer, there's always going to be a seller, and they're just basically doing like an on-chain swap. It's like I hand you $10, you hand me like I guess like 100 yen, no 1,000 yen, right? Because we're just doing like a swap, the net exchange of value is zero. Like I'm not really moving more value from my chain to your chain, and at the end of the day, the total amount of value that's available on both destination and source chain are still the same. Does that kind of answer your question?
Yeah, makes sense.
All right, so back to the topic of the hard fork problem, right? We have these validators, but again, their true incentive for them to be a validator is that like they make a financial gain, right? I don't think like I guess the goodwill in humans will always outweigh or potentially outweigh a huge amount of like financial incentives, right? That's why we always have criminals and things happen in history. Countries fight each other for resources. Yeah, we've seen it multiple times happening in history, and this is still the case. So that's a problem, and it's also very difficult to hold decentralized oracles accountable if there is a hack, right? Like because if we have a centralized exchange, a centralized bridge, it will be easy to say like, hey, wormhole, you fucked up, like please pay us back our money, all right? But if it's truly decentralized, then who's there to blame? It's just the network's down, right? There's bugs in the smart contract. No one is there to blame.
And in fact, wormhole did pay back the money, so.
Exactly,
Yeah.
right? So sometimes in a case, maybe centrality is better than decentrality, right? But then again, we're in Web3 where everyone's striving for like a decentralized future, which we might discuss about the true application of decentralized future in another like workshop or something. So yeah, like it is just truly at the moment like a truly hard problem to come up with a good design of a secure bridge system. At the end of the day, even if you come up with a beautiful protocol, you still need to make sure that it has good finality time, it has good implementation and ease of use, and it has like strong assurance and security in the design of the network. Like once you hit all those points, then it is like a good bridge, right? That's why so far everyone's striving to like build a good bridge, but no one so far yet has truly come up with the best bridge. Yeah. And at the end of the day, program bugs, security flaws, yeah, always a troubling problem. So we need you guys, like we need you guys to go into research, go into study about like how we can build a better future with crossing bridges. And I hope that this is like a starting point for you guys to understand how bridge works. Next time when you're swapping, I guess, assets across different chains, you kind of understand what's happening under the hood and you will not get scammed.
Question. So wait, what was wrong with the one-to-one system again? Like, isn't that how the real world works?
Like this was.
Well, yes and no, right? Because like if you're trying to like think about if you have like a new bridge and you're trying to draw liquidity from other bridge for it to like kickstart, right? If you have no liquidity on chain, then how can you draw liquidity from other chains? You simply can't.
But it's like people believe in you, so your value goes up.
Well, yes, but that's like a very arbitrary thing, right? Like for example, when let's say the United States of America first began, right? We brought value from the Great Britain to like this land, this magical land. Before then, there's not a lot of research there at all.
But there's must be like you can just like do cross-chain swap, but the tag rate or the exchange rate changes, right? Like so based on the supply and demand. Right? Does that not work?
It's not a very direct transfer of value, is it? Like, of course, you can say like, oh, we can gather up a community and let's hype up Dogecoin. That's what Elon Musk did, and essentially that is what happened.
Liquidity provider on both sides, essentially, right?
Yeah.
It's just like when you transfer from like China to US, right? Like essentially the banks on either side is acting as liquidity provider.
So that is like what you're describing is essentially what one-to-one do. And like what I personally believe about the true bridge system is like I guess like the airplanes and
Right.
I can ship gold bars from China to America without having to ship back the equal amount of gold bar from America to China. That is like
so you're describing like you destroy the asset on one end, mint on the other side.
Yeah, not necessarily destroy the asset, but just truly moving the liquidity from one like chain to the other. That is a true bridge in my own definition.
Right now, like one-to-one seems to be the most secure. It's just like
it's definitely secure, right? Because it's not really truly doing the job of
right. So you're missing a on-chain on-chain notion of asset, right? Then you can just use Bitcoin.
That's also not the case though, because like how can you integrate Bitcoin into like an arbitrary like blockchain?
Then you need more validators.
And then you're going back to the same problem as proof of stake, right? Like, yeah. Okay. So yeah, I hope that kind of give you guys like some like thoughts about bridges and blockchain. Any questions?
Okay, another way to think about this is like, okay, then let's talk about like like bridges that does actual value transfer, right? They can be hacked or like incentive is not aligned. But isn't this the same problem as Web3 security, right? Like security is not to design the things that's unhackable, but rather it's like makes it difficult to hack. But like the proof of stake essentially makes it difficult to hack.
So it's all about probability multiplied by like however, like I guess the value of damage will be, right? And as long as it's like lower than a specific threshold, then if you study stats, you would know this. Then it's not really feasible for the attacker to hack the system. But as we discussed in the current design, right, unless we somehow, I guess, like one idea is potentially to, I guess, like break up the total amount of funds into multiple smaller accounts, just like how in a bank system, right? All the smaller banks only hold some little amount of money in their local branches, while it's like the national banks have this large, heavily guarded like safe that holds all the assets. Like even if one bank got robbed, not all the money will be lost. That is one potential design that people are thinking towards that may reduce the, I guess, like the potential reward per hack. And that might be a better design.
It's just like multiple small printers.
Multiple escrow accounts, multiple dynamic way to allocate the money across these escrow accounts, such that if an escrow account like successfully got hacked, and not all of that would be compromised. Yeah.
Okay. Interesting. So what's the most promising bridge startup thing?
There is a lot, right? Because like, again, the industry is so new. There's like new protocols coming up every single day, right? We're still evaluating whether or not they work. Even if it all looks good on paper, it's still my shit of pants like in real life. That's just how things are. Right. So I guess that is the end for the bridge section. And before we end our, I guess, recording, I would like to announce that we have this Filecoin virtual machine hack day coming up on February the 26th. It's an event that goes from 9 a.m. to 6 p.m. that tells you and teaches you about what the Filecoin virtual machine system is about. And we encourage everyone to come. There's going to be free food, free merch, free everything. So yeah, please swing by.
We have so much money to spray, so we'll be spraying money.
Yeah. Thank you guys for coming. Hope you guys had a good time.
It's on his job. Yeah.
Are you going?
Watch first sucks.
This network thing bad.
Dude, I just gonna attend. Like.